Okay, good evening, everybody.
Good evening.
And welcome to another session of organic chemistry. In today's session, we are going to finish up on our discussion on stereochemistry, which is from chapter 5 of your book. When we left on Tuesday, we defined for you what is stereochemistry. Then we gave you examples of the schematic of isomers, different types of isomers. Then we discussed chirality and enantiomers. Also discussed configurational stereomers. And finally, we discussed mesomolecules. So for today, we are going to finish up this chapter with a discussion on resolution of racemic mixtures, optical activity, and then during the course of the discussion, we will briefly discuss the impact of stereochemistry on organic chemical reactions. Okay, I'm also sure that you guys want us to go over the quiz questions. Okay, so let us do that before we start our discussion. Okay, what I want to do, I want to start with the easiest question here, question number 3. Sipora, can you read this question first? Okay, thank you. Okay, so what you have to do here is to draw the Fisher projection for this compound here, 2R, 3S, 2-bromo, 3-methylpentane. Okay, so as you can see here, the first thing you need to do before you assign the absolute configuration, which is the R and the S, draw the structure of this compound first, just the basic structure for this compound. We have pentane, is the base name. So we start with CH3. And then on carbon number 2, we have a bromine atom. There's bromine here. That means hydrogen goes here. On number 3, carbon number 3, you have a methyl group. Then hydrogen here. And then you make up the difference with 2 other carbon atoms, which will be your ethyl group, because you have 5 carbons in the longest carbon chain. That will be 2-bromo, 3-methylpentane. Now the question is this the right molecule you are supposed to draw? Keep in mind you got to make this 2R and 3S. So let us number this molecule here. It's 1, 2, 3, 4, and 5. The first question I want to ask you, how many chirality carbons or chirality centers does this molecule have? 2. Okay, where are the 2? Carbons 2 and 3? Okay, very good. That is correct. Okay, so let us start to assign, use the Can-Ingo pre-log system to assign priority and then assign the absolute configuration for each of the chirality carbons. Okay. Take this out. Okay, so now in this case we have 2 chirality carbons here, or centers. So you want to focus on one chirality carbon at a time. Okay? So let us focus on carbon number 2. Assign the priority to the groups or atoms attached to carbon number 2. Okay, so which is priority A? Bromine, based on atomic number. Okay. Which is priority B? According to this carbon here, this group is attached to that carbon. Consider this a group by itself attached to this carbon here. Okay, and then the other group is this here. And of course you have bromine and then you have hydrogen. So which is priority B? The bigger group, this here. Okay. Based on what? You go to this carbon here, right? Okay, this carbon, you also have carbon here. So you cannot make a decision based on the first carbon. Then you go to the next attachment. In this case, this carbon is attached to 2 other carbon atoms. On the other hand, this carbon is only attached to 3 hydrogens. Therefore, this carbon here has priority. Okay? So we say that is B. Okay. Finally, of course, hydrogen will be D. Okay, so now what do we do now? You make a circular motion from A to B to C. Ignore group B. Ignore group D. Okay, so if you want to make that circular motion, we go from A to B, and we completely ignore D. Of course, I'm sorry about that. This is supposed to be C right here. We ignore group D. Come to C. Okay. So if you do that, what is that motion? Motion is what? Okay. Is what? Clockwise motion. But that is the motion. The motion is clockwise motion. However, which means that this will be R, right? However, because the group of lowest priority, D, is doing what? It's coming at you, so therefore you have to switch. Okay? Because the group of lowest priority, R, this here, is coming at you, so you have to switch. So in reality, the absolute configuration of this carbon is therefore S. You follow that? Okay, now, if it is S, if the configuration of this carbon is S, what do they tell us to give? It's R. That means what to do? Switch it. For to have S, that means the bromine will be here and hydrogen will be here. No, now we have this is S. Okay? Now let us now focus on this carbon here, carbon number 3. Let us focus on carbon number 3. For carbon number 3, this will be a group attached to carbon number 3, which is this carbon here. And this will be another group attached to carbon number 3. And of course, you also have a methyl group and an hydrogen attached to carbon number 3. So therefore, now let us make our assignment. Priority assignment. Where is A? Which is A? The top one? Okay, very good. Very good. B, ethyl. B is ethyl. And C, don't be consistent. Yeah. C is C is methyl. I took it off and put it back, right? Okay, I was laughing. Okay, C is methyl, and of course D is hydrogen. So what do? I make my motion from A to B to C. Go from here, completely ignore group D, okay, and that motion is what? Is counterclockwise. That is a counterclockwise motion, and that would be ordinarily would be what? S, okay? Now, however, is there an however here? The group of lowest priority, which is hydrogen here, is coming at you. So therefore, according to the RU5 rule, that group should be going away from you. So since we are violating the rule, we have to switch. So we switch. So that means that is actually R. Okay? So this carbon therefore is R. Okay, let's take everything out. So this is R, the way it is right here. But what do we need? We need S. So therefore, what do you do? Switch it. Exactly. So the way you do this, just the first thing you do, just as we've done here, go ahead and write a structure. Assign absolute configuration to the appropriate carbons. If it is wrong, then just switch it. Okay? And this will be the Fisher projection for this molecule. Yes?
So Fisher projection is going to be the dash line?
No. I did say that last time. Fisher projection does not show a dashed line or a wedge for Fisher projection. Fisher projection is just a straight line. It's almost like your calculate structure, okay, with some kind of condensed formula. Okay, but with the Fisher projection, all the bonds in the horizontal position, you assume they are coming at you. That is very important. And the bonds in the vertical position, you assume they are going away from you. Okay? Okay. So, yes.
If you have drawn it as like 5 straight carbons, and then have the H and the Br on the top, and the H and the CH3 on the bottom.
If you have to make sure that the those two carbons, as long as the chirality carbons are in your Fisher projection, okay? As long as they're in the Fisher projection, and you assume that any group, horizontal group, is coming at you, that's fine with me. But the way you have it is going to be very difficult for you. In other words, you draw the pentane in this group here, well, that's fine. But keep in mind, as long as the bond, horizontal bond, is coming at you, okay, and the vertical bond are going away, that's all you have to follow. Okay? Okay. Let us do the next one. I will do number 2. Okay. Agize, can you go ahead and read this first? Okay, thank you. Okay, with number 2, this question says determine the absolute configuration of the chirality center in each of the following molecules. Okay, let's say this is molecule A and this is molecule B. All they want you to do here is to determine the absolute configuration. Where's the chirality carbon here? Let me number this. Let's say this is 1, 2, 3, and 4. Where is the chirality carbon in this molecule?
3.
Carbon number 3. Very good. Very good. Excellent. So carbon number 3 is your chirality carbon. Okay, so let us determine the absolute configuration for that carbon. Now to do this, keep in mind the first thing I tell you to do, you focus on the chirality carbon. And you want to make a Fisher projection for all of the groups attached to that chirality carbon. Keep that in mind. Okay, so I'm going to do a few gymnastic operations here, using myself as a cartoon. Okay, so imagine that I am going to stand between this bromine and this chlorine. Okay, and this is my head right here. Okay, this is my nose, right? Looking directly at this here. So I am here. Okay, looking directly right there. Okay, that means if I'm looking directly here at this carbon here, this here is my left leg, okay, and this here, if you can believe that, this is my right leg, okay? I'm standing right here, between this bromine and this chlorine. Okay? Looking directly at this carbon. This is my nose right here. Okay, so let's look at let's do the Fisher projection for that carbon and the groups attached to it. What is on my right? What is on my right? What is it? Chlorine. Okay, very good. Everybody agree? What is on my left? Bromine. Don't forget, I'm standing between the bromine and the chlorine. What you need to do, you position yourself so that two groups will be coming at you. That is what you want to do. Okay? You want to do it. Position yourself anytime so that two groups will be coming at you. Okay. Therefore, what is above my chest? This group, right? What is below my chest? CH3. Very good. Okay, now what we've done here is to write it. Take a look at this chirality carbon here, and then write this chirality carbon so that all of the 4 different groups attached to it will be in a Fisher projection. Bromine and chlorine coming at me. This group right here with a carbon-carbon double bond going away, and the metal also going away. So now let us assign absolute configuration. Priority first, right? What is priority A? Bromine. Based on atomic number. Priority B? Chlorine. Now, about priority C. The alkene. Very good, excellent. Now in this case, you have this carbon here. You also have a carbon here. Then you ask yourself, this carbon is doubly bonded to this carbon. Anytime you see a double bond, assume that you have 2 single bonds. In other words, this carbon here is attached to 2 other carbon atoms. That is what that would be. If you see a triple bond, that means it is attached to 3 other atoms. Okay? Okay, so in this case, this carbon is attached to 2 other carbon atoms here. Therefore, it has priority. So this is C. And then this is D. Okay, so we make our motion. We make our motion from A to B to C. Ignore group D. And what is our motion? Counterclockwise. Which is supposed to be S. Okay, do we need to switch?
No.
No, we don't have to switch, because the group of lowest priority, which is methyl, is going away from us. Okay, so the absolute configuration here is S, and that's what they tell you to do. Okay, so now let us do the next one here. So compound B. Okay, let me go ahead and number the carbon in this molecule. This is carbon 1, 2, 3, and carbon 4. Okay, how many chirality carbons do we have there? 1. Where is it?
3.
Number 3, carbon number 3. Excellent, very good. Okay, this carbon number 3 is your chirality carbon. Keep in mind, for chirality carbon, that carbon must be attached to 4 different groups or 4 different atoms. Okay. Now let us assign. First thing I need to do is what? What do I need to do?
You need to assign priority.
Before I assign priority, what do I do? Make it into a feature, exactly. Give a feature representation of this carbon right here. Okay? Okay, so I want to do a feature representation. Now, what I want to do, I want to position myself so I see these 2 groups coming at me. Okay? I'm going to do whatever you can to position yourself to see those 2 groups coming at you. Okay, so what I will do here, I am going to say my head is right here. My nose is here, right? You know that I'm facing that, between them, I am facing that, so I'm then right here. I am between this OH and this hydrogen. Right? I'm facing up, right? Like this. Okay, so if I do that, so if I do that, this here will be my right leg, right? And this here will be my left leg. Okay? And just here. Wait a minute. Am I right? Doing like, no. I'm doing like this. Okay, I got that wrong. This is my left. This is my left leg. And this is my right leg. Okay, I'm looking like this, right? Okay, left is here and right is here. Okay. Now, I will position myself. Let us now do a feature representation for that carbon. What is on my right? OH, very good. On my left, therefore, is hydrogen. Okay. What is above me, above my chest? This group right here. Okay, very good. So you have that CH2. So this group right here, this is above my chest, CH2, and no, let me go ahead and write it down. Okay, what is below my chest? Below my chest, this group here, right here. This here, right? Carboxyl group. Okay. So therefore, that is this here. Okay. Okay, now we assign the priority. This is A. Where is B? The carboxyl group, exactly. The carboxyl group, because you have carbon here attached to 2 oxygen here and attached to this oxygen here. Okay? Whereas this carbon is only attached to a carbon. So this is priority B, and then this is C, and of course this is D. So now we make our motion from A to B, ignore group D, to C. And that motion is what? What kind of motion is that? Clockwise motion. Which is R. Okay, do we need to make a switch? Yes. So we switch, which is S. So that means this here is S. Absolute configuration of that carbon is S. Okay? Are you all follow that? Okay, so let us go to the last one. Okay, Robin? Okay, you're trying to hide from me. Can you read this? Chirality. Okay, thank you. So here we say how many chirality centers or stereogenic centers are present in the following molecules. Okay, anybody know how many? How many? 3? Okay, well, let's go ahead and number this here. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay? Okay, which are the 3 carbons? 2, 3, and 4. Okay, very good. So 2, 3, and 4, this here, and this here. Those are the chirality carbons. Okay. Now, okay, what is the hybridization of each of those chirality carbons? sp3. Okay, that's what this is asking you. sp3. But keep in mind, our focus is on the sp3 carbon. When you have a chirality center, that carbon will be an sp3 carbon. Okay, now, let us do one problem here before we leave and go to today's lecture. I want you to assign absolute configuration to carbon 3 and carbon 2. Okay? Assign absolute configuration to this carbon here and this carbon here. Okay, let me show you. Okay, we know these 2 groups. This one is coming at you, this one is going away. So what I want to do, I will position myself between here. Okay? I will position myself. Once again, I say I am right here. This is my nose, right here. And then I am here. I'm actually bending my back, right? positioning myself right here. In that case, I'm looking directly right this way. In that case, look at here. That is my left leg, and this is my right leg. It's almost as though I am doing this. Just doing this. Okay. And here, but the point here is that I am focusing on this carbon right here. Okay. Facing this carbon. Okay. Let's do the feature projection for that carbon. Okay, what's on my right? OH, very good. On my left? Hydrogen. Okay, above me, okay, let me bring this down a little bit. This group, okay, over my, above my chest. So let me, say OH, say H, and then we have this here, this hydrogen, this OH, and then with this here. Okay, below therefore will be the rest of the group right here, okay? This H. At this point, my focus is only on this carbon. Keep in mind, I am focusing on this carbon. And this contains something else. We don't have to worry about that for now. Okay. So now, focusing on this carbon here, let us assign the priority. Priority, this is A, right? Okay. Which is B? On top? Okay. Therefore, this is C, and this is D. Okay. Now I make my motion from A to B to C. Ignore group D. And what is that motion? What is that motion? Counterclockwise. Which would be, ordinarily would be an S, but because the group of lowest priority is coming at us, which is D, this group right here, hydrogen, we have to switch. So it's actually R. Okay, so therefore this is R. Okay? Okay, let's do one more before we go to today's presentation. Okay, let us do this one here. This carbon here. Okay, once again, I want to position myself. Okay? Okay, I will take advantage of the fact that I know this is here coming at me and this is going. So I want to position myself between the hydroxy and the hydrogen. So I will say, okay, I will be right here. Once again, I am going to be facing this with my nose right here. Maybe I should make it this way. I will be standing between them, looking directly here. That's my nose right here. Okay, and then I'm here, facing up. Okay, facing up. That means this here, my right leg, and of course my left leg. So I'm doing just this leg. Okay? Okay, now let us do the fissure. What is on my right? What is on my right? OH? My left? Above my chest? Okay. Will be the aldehyde group. And then below my chest, okay, will be this group right here. All of this will be below my chest, right? Okay, so therefore I have COH, hydrogen, attached to another OH, hydrogen, and then attached to something else, so we don't worry about that for now. Keep in mind, our focus is on this carbon right here. Okay, which is this carbon right here. Okay, so we assign the priority. This is A. Now, which is B? The aldehyde group? Okay, very good. This is B. And this group here, therefore, is C. This group is C. And this hydrogen is D. So we make our motion from A to B to C. Ignore group B. Okay, that motion is a counterclockwise motion. Which is supposed to be S. However, do we switch?
Yeah.
Because the group of lowest priority, in this case, this is hydrogen, is coming at you, so you make a switch. So this becomes R. So therefore, this here is R. Okay, so I will leave you to do this one when you get home. Okay? Okay, so at this point, let us start our discussion for today. And then we'll finish up with chapter 5. And on Tuesday, we are going to start chapter 7. Okay. Okay. Okay, I told you earlier that today we are going to discuss resolution of racemic mixtures and optical activity, and then, of course, during the course of our discussion, we shall also discuss the impact of stereochemistry on organic chemical reactions. Let's take a look at this molecule here. We want to start with the racemic mixtures. But to do that, there is another topic I will briefly want to go through before I introduce the concept of racemic mixture, and that is ProChirality molecules and ProChirality carbons. ProChirality molecules and ProChirality carbons. Now let me give you the definition of these two here. For the ProChirality molecules are those that can be converted, those I'm sorry, those ProChirality molecules are, let me change that. ProChirality molecules are achiral molecules. Achiral molecules, in other words, molecules that will superimpose on their mirror images. Achiral molecules that can be converted into chiral molecules. Of course, chiral molecules, those are the molecules that do not superimpose on their mirror images. Okay? So ProChirality molecules are achiral molecules that can be converted to chiral molecules by a single chemical reaction. By a single chemical reaction. Okay? That is the definition of ProChirality molecules. Now let me give you the definition of ProChirality carbon. ProChirality carbon are those non-chirality carbons that can be converted to chirality carbons by a single chemical reaction. By a single chemical reaction. Okay? So now let us give you an example of the ProChirality molecule. See what kind we have. Supposing we take a look at this molecule here. Take a look at that molecule here. This carbon here, what is the hybridization of this carbon right here? sp2, very good. That is an sp2 carbon. Okay, so I'm going to show you this model here. Imagine that this is your sp2 carbon. Okay? Keep in mind the sp2 carbon, because of its geometry, we say it has a trigonal planar geometry. Which is to say that all of the atoms that are attached to this carbon are on the same plane. Okay, think of this as oxygen. Think of this as oxygen. Okay, think of this as the ethyl group. Think of this as the methyl group. This carbon, this, and oxygen, they are all on the same plane. Okay? So therefore, we say there are two faces to this molecule. If you look at it from this side, we say that is one face. If you look at it from this side, we say that is another face. Okay? Or you may want to look at it here. If you look here, this is how it looks here, right? See one face, comes here another face. Okay? Okay, now. If you take a look at those two faces, how do we distinguish them? To distinguish those two faces, we assign priority to the atoms that are attached to this central carbon here, the sp2 carbon. Okay, and if you want to assign priority, this is A, this is B, and this is C. Okay, so therefore we move our clockwise motion, and we move from A to B to C. What kind of motion is that? Clockwise. Okay, so therefore, the side of the molecule, or the face of the molecule that gives you a clockwise motion, we call that an RE face. We say that is the RE face. Okay? In other words, if I look at this here, okay, I draw it, and I am able to move from A to B to C, that would be considered, and that is clockwise, I will say that is the RE face. Now supposing we look at the other face, that would be opposite. If you look at the other face, okay, one face is looking here. If you then come here and look here, okay, if you look here, the methyl is will be on your right, ethyl is on your left. But if you then look here, ethyl is on your right, methyl is on your left. So therefore, let us represent that molecule the way we see it, that face. So those are the two faces. Now, I then assign priority again to this. This is A, of course this is B, and this is C. Assign priority to the atoms attached to the sp2 atom. And then you make your motion, go from A to B to C, and what is that motion? Counterclockwise. So your counterclockwise the phase that gives you the counterclockwise motion, we call that the SI phase. Okay, so we have two phases, the RE phase, in other words, the phase that gives you the clockwise motion, and the SI phase, which is the phase that gives you the counterclockwise motion. Okay? Now, why do I tell you this? If you want to perform a chemical reaction on this molecule here, the product will be different depending on the phase from which this molecule is attacked. Okay? So let us see here. Okay, so this is the SI phase. Take this out. Okay, this is the SI phase. Okay, so we simply just now have this here. This is RE, and this is the SI. Okay. Now, supposing I want to perform this reaction. This reagent, we are going to be using it later during the course of this semester. If I take this here, I take what I call lithium aluminum hydride, step 1, and then step 2, I add what I call hydronium ion. So what the lithium aluminum hydride does is to supply a negatively charged hydrogen atom, which we call hydride. It will supply an hydride to this molecule. So if this hydride comes from the RE phase, you get this product.
So why do you have 1, 2? What does that mean?
Oh, okay, you add the lithium aluminum hydride first, then you add the hydronium ion later. That's what that means. But when we get to chemical reaction, we'll explain some more about that. Okay. But at this point, just assume that in this reaction, we are going to introduce an hydride on this carbon here. So, a negatively charged hydrogen atom. Okay, which is that?
Is the I there on purpose?
Where? This here? This is the hydride. Oh, that is the name of this here.
Oh, those are electrons. Oh.
Okay, those are electrons. Okay. Yeah, okay. Anyway, so we get this. We get that molecule. That is the product we get. If we attack from the RE side, the RE phase, on the other hand, if we attack from the SI phase using the same reagents, also lithium aluminum hydride, get this. We get those two products. Let us call this product A and call this product B. Those are two different products, depending on the phase from which the hydride approaches this molecule here. If it approaches from the RE phase, we get this product, compound A. If it approaches from the SI phase, we get compound B, yes. No, then just take this reaction as providing both this hydride and this here, just for now. When we get to later on, we'll show you the reaction mechanism. Okay? Think of this here, this reagent, as complementary reagent. They are producing hydrogen, hydride and hydrogen, yes.
Does it matter how we structure it?
Good one.
Like, how do you know to put OH or CH2 and CH3? How do you know to put those two coming at you?
Okay, very good. Okay, when this hydride comes in here, the hydride is approaching this. Okay, approaching this molecule from this side. What it does, it pushes everything. It pushes everything back. Okay? Because now this carbon is going to become an sp3 carbon. Because it's going to become an sp3 carbon, that carbon will be in the middle of a tetrahedron. Okay? So it comes in, so everything is pushed back. Okay? So therefore, by necessity, you have to draw this tetrahedral geometry right here. Okay? In other words, this oxygen is pushed back, down, and this is also pushed down, and then also this metal is pushed down. But by virtue of the fact that it's sp3 carbon, they assume the tetrahedral geometry. Okay. So anyway, you get compound A and B. You find out, let us do the absolute configuration for compound A. Okay? What is the absolute configuration for compound A? I am going to place myself right here. I'm looking directly, I'm between this here. Okay? My leg are there, facing that, right? Okay, so on my right is OH. On my left is this here. On top of me is hydrogen, and below me will be metal. What is the absolute configuration of this carbon? We have A, we have B, priority, we have C, we have D. Okay, so you make your motion is S, right? Very good. Okay, so this is S. Okay, let us determine this here. Once again, let me position myself right here. I'm facing this here. Okay, standing between them, my legs are here somewhere. Okay, I'm facing directly. So what's on my right? What's on my right? OH. Metal. Hydrogen on top. And what is the priority here? A, B, C, and D. So I'll make my motion. So that is clockwise. That means this is R. Okay? So these two molecules here, what is the relationship between them? Does anybody know? What is the stereochemical relationship between them? Enantiomers. Okay? Okay? So therefore molecules A and B are enantiomers. So if you approach this molecule from the RE phase, you get the S enantiomer. If the reaction takes place on the SI phase, the product you get is the R enantiomer. Anytime you get a reaction in which you now have a mixture, there is no reason to believe that the hydride will come here any faster than here, right? So you are going to get equal amount of both enantiomers. You are going to get equal amount of both enantiomers. Okay? So therefore, this here, this mixture of products you get here, we refer to as a racemic. Or another word for it is racemic mixture. Now what is a racemic mixture? It's a 50-50 of two enantiomers. Okay? 50-50 equal amount of two enantiomers. So anytime you have an equal amount of two enantiomers in a mixture, then you say you have a racemic or racemic mixture. Now, keep in mind at this point, each one of the enantiomer is a chiral molecule. This here is chiral. This here is also chiral. But the mixture, the racemic, this mixture here is achiral. Okay? Because you have both of them in there. Okay? Once you have the mixture, I'm sorry. No, I'm sorry. Let me take that back. This here is chiral, right? This here is chiral. It's also optically active. That's what I wanted to use. Optically active. And this is also optically active. So let me take back what I said before about the mixture is achiral. But the mixture is optically inactive. In other words, the racemic here is optically inactive. Okay? We will tell you why in a minute. The racemic is optically inactive, even though the individual enantiomer in that mixture, individually, they are optically active. Okay?
So you think the whole mixture is...
The mixture will be optically inactive. I will tell you what we mean by that shortly. Optically inactive. The mixture, the racemic, will be optically inactive.
Is the racemic same as the racemic mixture?
Yes, it's the same as racemic mixture. Okay? Anyway, so the point here, when you have this molecule, therefore, we refer to this molecule as a pro-chiral molecule. Because when we take a pro-chiral molecule, you perform this reaction, then you get a chiral molecule. This is also pro-chiral molecule. So when you take this molecule here, which is pro-chiral, in other words, you could perform one single reaction, and then you get a chiral molecule right here. Okay? Okay, now, so now you know about pro-chiral molecules, and then you know about racemic and racemic mixture. Now let us see here. Let's give you, oh, see, plenty of time. Okay. Let us now discuss pro-chirality carbon. Supposing we have this molecule here. Remember the definition of pro-chirality carbon that we gave you earlier. Supposing we have this molecule. If we can perform one reaction that will replace any one of these hydrogens here, okay, we are going to get a chirality carbon. Okay, so this carbon here is a pro-chirality carbon. Because let us assume that we do bromination. Remember we did bromination last time, chapter 3 and 4. Say we take bromine in the presence of light. And we told you that this reaction, this reagent, will replace an hydrogen that is attached to an sp3 carbon atom. Okay, so we get this product. Let us say we replace this here, bromine, hydrogen is still here. Okay? If we replace that, now what we have? We now have a chirality carbon. This carbon now becomes a chirality carbon. Therefore, we refer to this carbon here as a pro-chirality carbon, because that is the carbon that we replace the hydrogen attached to it, and then we got a chirality carbon. Yes.
Is there a trick to identify the pro-chirality carbon?
You just imagine that you replace one of the hydrogen with some of the atom. If you get a chirality carbon, then that's it. That's essentially what you have to do. Okay, now.
Like two halogens on there. Because it's still going to be a carbon.
If you replace one of the halogen, it will still be a pro-chirality carbon.
Okay.
Yes.
Okay, so first question, so it doesn't have to be a hydrogen?
No, it doesn't have to. Yeah, very good. It doesn't have to be a hydrogen. Yes. Now, supposing, in this case, what did we do here? We replace this hydrogen here. Supposing we replace this hydrogen, right? Do the same reaction. Okay? Now we get another pro-chirality carbon. Let us call this compound A, and this is compound B. What do you think is the stereochemical relationship between compound A and B? What is it? They will be enantiomers. They are enantiomers. Compound A and B are enantiomers. So therefore, the mixture from this reaction, will it be optically active or optically inactive? The mixture. Huh? Inactive, because you have a racemic. Because there is no reason to believe that this bromine will replace this hydrogen any faster than it will replace this hydrogen. So you will get equal amounts of the enantiomers. So this will be optically inactive. Okay? So now finally just one more thing and then we'll finish this chapter. No. One more thing, I will give you back 2 minutes. I will do 2 minutes. So far I have been telling you optically active, optically active, optically active. How do we really know that these enantiomers exist? Okay? We could determine optical activity by performing a simple experiment. Ordinarily, if you have a beam of light, like sunlight or your light bulb, you have the rays of the light goes in all directions. But if you pass that light through what we call a polarimeter, all the beam of light now has only one direction. Goes in one direction. Don't mind my line there. Okay? Goes in one direction. So now we say this is a plane polarized light. Now, and that's what we've done here. So now if you take a plane polarized light, you pass it through a sample that contains enantiomer. What happens? This light here will move, the molecule will move this light either in this direction, in the right direction, or it could move to the left, or it could move to the left. The degree or the magnitude of the deflection in terms of how far it moves the light, the magnitude we refer to as specific rotation. Okay? So if a molecule has a specific rotation, we say it is optically active. Okay? Now, if you have two enantiomers in the sample, what do you think will happen? As one of the enantiomers rotates the light to the right, which we call dextrorotatory. Okay, we'll give this a sign of plus. The other will rotate to the left, we call levorotatory, which will give a sign of negative. So if you have in the solution two enantiomers, just as one is moving to the right, the other will be moving it back. Then what happens? That sample becomes optically inactive. But if you only have one enantiomer in that solution, it moves, then you'll be able to read the dial to say, okay, it has moved this far. Then it is optically active. If you have two enantiomers, the difference between them, the magnitude of the rotation will be the same, but the direction will be different. One will rotate to the right, the other will rotate to the left. Now, can you tell which isomer can do that? No, you cannot. That is an experimental value. In other words, you could only determine what sign that rotation is by doing the experiment. Okay, so when we come back on Tuesday, we have finished chapter 5. When we come back on Tuesday, we are going to start chapter 7. Actually, chapter 7, what I will do, yes, what I will do, I am going to combine chapter 6 and 7. Okay, so I will be starting with chapter 7 on Tuesday. So enjoy your weekend. Yes, we have finished chapter 5. Yes. Okay, so you can see here, this molecule here we call lactic acid, rotates to the right, and this one rotates to the left. Those are two enantiomers. Okay? Okay.